Let's go ahead and get started in this very special episode of Physics 514 at a special time in a special place. Last class, just to remind you, we concluded our discussion of manifolds, and we decided that spacetime was a four-dimensional manifold, which in particular meant only that the points in spacetime can be smoothly labeled by coordinates. So, for example, xi or x mu could be a coordinate system labeling points in spacetime. And if you have two different coordinate systems, say x mu and x mu prime, then the interesting thing to start thinking about is the coordinate transformation, where we take physical quantities written in terms of the x mu coordinates and then rewrite them in terms of the x mu prime coordinates. And of course, these x mu prime coordinates can be regarded as functions of the original x mu coordinates. And we decided that we need to write the laws of physics in a way which is independent of the coordinate system that we use to write down those laws. So we need to start with a careful investigation of how the various quantities that we use in physics transform under these coordinate transformations. So, for example, we saw that the simplest possible way that an object could transform under a coordinate transformation would be to not transform at all. So, for example, if we have a scalar function f, then that's just an assignment of a number to each point in spacetime, or each point on our manifold, which could be written as f of x mu in some coordinate system. And if we wish to understand how that function looks in a different coordinate system, then it's related in the obvious way. So, for example, if we were to write that function in the primed coordinates, then that would be related to the function in the unprimed coordinates simply by regarding the x mu primes as a function of the x mu's. And the scalar function is something that you're probably intimately familiar with from your studies of vector calculus and so forth. But there are various generalizations of this, which go under the name of tensors, which are much more general sorts of objects that can transform in much more interesting ways under coordinate transformations. So the first non-trivial example of a tensor is a vector. So what is a vector? So if our manifold is d-dimensional, then a vector is a set of d quantities, or d functions of the coordinates, associated with each coordinate system which transforms in the following way. So if v mu is our vector written in the x mu coordinates, so this is a set of four or d functions of the x mu's, then if we want to write v in the primed coordinate system, then v mu prime as a function of the x mu primes is related to v mu by the multiplication by the Jacobian matrix. So dx mu prime by dx mu times v mu summed over mu from 0 up to 3 or from 1 up to d, depending on the dimension of your manifold and what conventions you're using for the value of the index mu. And v mu here, of course, is regarded as, well, is a function of the x mu's, which can be regarded as functions of the x mu primes, of course. And a vector also has another name. So a vector is also referred to as a contravariant vector, where contravariant here is the word that we use to refer to an upper index, as opposed to covariant, which refers to a lower index. And it's also known as a 1, 0 tensor. Whereas a scalar, I remind you, is a 0, 0 tensor. Okay. Now, although it might not be 100% obvious, yes, question.
Is this a fundamental definition of a tensor? Of a vector? Or does it transform like this to other quantity invariant?
This is, so there are many different ways that one could define a vector. This is how I am choosing it to define it in this class. In your vector calculus classes, you met a definition of a vector that was somewhat simpler and was only working in flat three-dimensional space or two-dimensional space. There are other much more abstract definitions of the vector. So there are many, many different ways of thinking about vectors as geometrical objects. I'll describe in class today 3 different ways of thinking about vectors as geometrical objects. I present to you this as the definition of a vector because I think it's probably the most straightforward for someone coming from a physics point of view. If you were to take a math class, some advanced math class in differential geometry at the graduate level, they would come up with a much more abstract definition of a vector, which is all well and good, but a little bit would be overkill for our purposes. Yes, question.
Although it's written in upper index, parameterization makes me physics.
That is correct. Yes, that is an important point. So not every quantity which has an upper index is a vector. So you need to keep careful. Usually, our Einstein summation convention is constructed precisely to make things easy when we're dealing with quantities that transform in appropriate ways. But of course, x mu, even though it has a single upper index, it's a set of 4 quantities, 4 functions, but they don't transform as a vector. However, we will see that there are various things that we construct out of x mu that do transform like vectors. Perhaps I will continue with my discussion of vectors, and many of the questions that you two have asked will be addressed in various different ways in the next few minutes. Let me we'll spend a little bit of time discussing vectors because I think it's important to get a bit of intuition for them before proceeding on to the slightly more unfamiliar tensors. Any other questions before I continue? Okay, good. So, now this, of course, as I said last time, is just a generalization of our notion of a vector from multivariable calculus. So, for example, we're used to dealing with vectors in flat Euclidean space. So we're very familiar with dealing with vectors, say, in three-dimensional Euclidean space. So what do we mean by a vector in three-dimensional Euclidean space? Well, we usually write a V with a little vector symbol over it, which stands for a column vector of 3 quantities. And we usually think of that as a little arrow, if you like, at pointing away from the origin. And it's important here to distinguish between 2 different things. So when we write the symbol V with a hat on top of it, we're referring to a geometrical object that has some meaning independent of whatever coordinate system you use to describe that vector. Whereas when you write these 3 symbols here, V1, V2, and V3, you're really just writing the components of that vector in a particular coordinate system. So in the definition that I gave above for a vector as a 1, 0 tensor, these V mu's should be regarded as the components of a vector in a particular coordinate system. But what I really want you to do is think of a vector as a geometrical object which has a meaning independent of whatever coordinate system we're writing it in. And the rule that I have given above is just the rule for how these different components transform when you go from one coordinate system to another. So let's see what that looks like just in the very simple case of vector calculus when we're studying our familiar vectors in three-dimensional flat space. So, for example, if you just take your vanilla vector in R3 and you imagine doing some rotation, so under a rotation, say where the three coordinate axes x, y, and z get rotated in some way, where R is some 3x3 rotation matrix. So what do we mean by that? So using Einstein summation notation, we would write that as xi going to some xi primes, which are equal to r I prime j xj, where r I prime j is the set of 9 quantities that make up the 3x3 rotation matrix. So under this rotation, how do the various components of the vector transform? Well, they go to r times v. Or in component language, we would say that the VIs, when written in the new coordinate system, take the form of r I prime j times vj. And so you can see that this R matrix, this rotation matrix, is the Jacobian matrix dxi prime by dxj, or what I call dx mu prime by dx mu, using the mu symbol for the index, the Greek index rather than the Roman index. So you can see that in the case where my coordinate transformation is just, can you guys see back there? Here, let me scroll up a little bit. In the case where my coordinate transformation is the familiar rotation of three-dimensional space, the definition that I've given for a vector is precisely the usual way that the components of a vector transform when you do a rotation. Likewise, in special relativity, you consider what are known as Lorentz vectors. A Lorentz vector is a set of 4 quantities, v mu, which you could arrange into a column vector, v0, v1, v2, v3. And under the Lorentz transformation, which takes the coordinate x mu to lambda mu nu x nu, this vector just transforms by multiplication by the 4x4 matrix, which describes the Lorentz transformation. I guess I should call that a mu prime. Now, in your classes on special relativity, you probably encountered Lorentz 4 vectors. For example, the energy momentum of a particle transforms as a 4 vector. The current of a particle transforms as a 4 vector, the 0th component of which is the charge density, the other 3 components of which are the current, and so on and so forth. So in both usual vector calculus and in special relativity, you've already encountered vectors. They're the objects that transform in these very simple ways under rotations or Lorentz transformations. And the definition of a vector that I have given above is a definition which now accommodates more complicated coordinate transformations. It doesn't accommodate the proper spelling of the word accommodate, I think. But aside from that, it does accommodate more interesting and, in particular, nonlinear coordinate transformations. In particular, it accommodates the sorts of coordinate transformations that involve acceleration rather than just boosts, which, of course, are the sort of coordinate transformations that, by the equivalence principle, are going to be interesting in our description of gravity. So now we know that the components of a vector transform not just by the multiplication by a rotation matrix under a rigid rotation of the axes of flat space, but they transform by the multiplication by this Jacobian matrix, the matrix of partial derivatives, under a more complicated coordinate transformation. And as I said before, what I really want you to do is learn to think of a vector as a geometric object which has some sort of intrinsic geometric meaning independent of any particular coordinate system. So it's a geometric object whose form will just look different in different coordinate systems. So even though, for example, a vector that points in the x direction might look very simple in the xyz coordinates, would look very, very complicated in polar coordinates. Perhaps in your lives you've written the vector that points in the x direction in its term in terms of the basis of vectors in polar coordinates and learned that it looks rather complicated. They're still the same geometric object. And so what I would like to do now is start introducing ways of thinking about vectors in differential geometry, just to help us develop our intuition for vectors and for the various sorts of quantities that we'll be encountering that transform as vectors. There was a question in the back? Yes?
Yeah. How can you get linear transforms?
Well, any coordinate you could make any coordinate transformation you like. So for example, let's say that I'm studying the flat plane and I'm using the standard xy flat coordinates. There's no rule that says I couldn't label my points using a different coordinate system, where I label them by, I don't know, one of my coordinates is y, and the other is the arctange of x. Okay? There's no rule that says I couldn't use that coordinate system to label points on the plane. Now, vectors which look simple in one coordinate system might look rather complicated in another coordinate system. Part of the art of the subject is finding coordinate systems that will help you for solving whatever problem is at hand. And as we go through this course, we'll learn various techniques for finding such coordinate systems. For example, remember when we studied the equivalence principle, we thought about Einstein's elevator, which was which described a constantly accelerating reference frame. Where x prime was related to x by the addition of t squared. So it's nonlinear in the sense that it's not linear in t, that would be a boost, but rather t squared, so it describes some constant acceleration. I encourage you to go back, if that's still a bit mystifying, and work through the coordinate transformation that takes you from a constant gravitational field to a constant acceleration. Any other questions? No questions? Okay, let's continue. So how should we think about a vector? So, in your head, what I want you to do is think of a vector as an arrow attached to each point in space-time. Remember here that the quantities v mu are themselves functions of the x's. So they're functions of where you're sitting in space-time. So that means that the behavior of this vector could change depending on where you're sitting in space-time. So what I want you to do is I want you to think of your manifold. Okay, you've got some sort of curved geometry here. And you choose some point that you're going to look at. And you think about the plane which is tangent to that point. And you think of your vector as a little arrow which lies in that plane. And that's not even a bad approximation. In fact, if you work through any one of the number of various precise mathematical definitions for a vector, that's precisely what they're saying you should do. So what you do is you end up defining what is known as the tangent space at a given point, which is usually referred to if M is your space-time manifold and P is the point that we're looking at, then the tangent space at that point is referred to as T sub P M. And the tangent space is nothing more or nothing less than the set of all vectors attached to a point P. So this is an awfully nice picture to have in mind, but it's still a bit abstract. So what I would now like to do is show you that, in fact, in this class, we have already several times encountered objects which transform as vectors. And indeed, on the problem set that you did yesterday, you already encountered several times something which transforms as a vector. So here now is a typical and perhaps the classic example of how you might encounter a vector when you're trying to do physics. So let's imagine that we have some observer who is moving through space-time, and this observer moves on a world line. Now, in a coordinate system x mu, this world line is specified by four functions x mu of lambda, where lambda is a parameter that smoothly labels points on this world line. And then we could define the following quantity. V mu is the derivative of x mu with respect to lambda. So we take the points on this world line, regard them as functions of lambda, this is how we parameterize this world line, and take the derivative with respect to lambda. So what is the physical interpretation of that? Well, if you have some world line going through space here, then V mu, which is dx mu by d lambda, is nothing more or less than the vector which is tangent to the world line. So this is referred to as the tangent vector to the world line x mu of lambda. Now, I claimed that this was a vector, so that means I need to show you that it transforms in the correct way under a coordinate transformation. So to check that this is a vector, let's compute its components in a different coordinate system. So in a different coordinate system, so in the x mu prime coordinates, the path, or the world line, that we're considering is given by thinking of the x mu primes as a function of the x mu's, and then regarding those x mu's as a function of lambda. So that's x mu prime of lambda. And v mu prime, by definition, is dx mu prime by d lambda. Okay, so how is that related to v mu? Well, we just use the chain rule. So the x mu primes can be regarded as a function of the x mu's, which are themselves functions of lambda. So the chain rule then states that this is the sum over mu of dx mu prime by dx mu times dx mu by d lambda. That is the chain rule. And we recognize this as the Jacobian, which appears in the definition of the vector. And the second guy here is just the components of the tangent vector in the x mu coordinates, rather than the x mu prime coordinates. So this is dx mu prime by dx mu contracted with v mu, which of course is the correct rule for the transformation of a vector. So this application of the chain rule is hopefully not terribly mysterious to you. If it is, I recommend that you quickly practice it so that it is not mysterious to you. This is a manipulation that we will use again and again in this class. Any questions? Yes?
What's the meaning of if dt d lambda is equal to 0? If you're stationary in time.
If you're
Stationary in time.
If dt by d lambda is equal to 0? There are certainly geodesics where dt by d lambda is equal to 0. That would be a space-like geodesic, describing a world line that moves faster than the speed of light. There's certainly nothing wrong with considering such a thing. It's not a realistic observer with finite mass, of course, couldn't travel along such a geodesic, along such a world line. But you could certainly talk about it, and there's still certainly a tangent vector associated with it. Yes, good question. Any other questions? I see a few mysterious looks. Maybe they're just looks of tiredness. It's at the end of the day. Okay, please interrupt me. Let me know if you have any further questions. So, this example gives us a way of constructing a vector that's attached to each point on a line. It's just the tangent vector to the line at any given point. And indeed, if I wanted to give a precise definition of the tangent space, if this were a math class, this in fact is the definition I would have started with, I would define the tangent space to be the set of all tangent vectors of paths that pass through a given point P. This is a physics class, so I started with a picture and with some words and didn't prove anything. But if this were a math class, that's how I would have defined the tangent space. If this were a math class, it would have taken me like 5 freaking lectures, though. So it's good that it's not a math class. Now, the example that I just gave is an example of a vector that's attached to each point on a line. But, of course, in general, we could also imagine a vector attached to each point in space-time. Sometimes we have a special name that we associate with a vector attached to each point in space-time. We call that a vector field to distinguish it from the idea of a vector attached just to each point on a line or just attached to a particular point in space-time. Although in general we'll be a little sloppy and we'll just call all of these things vectors. In fact, when I say vector, you should generally assume that what I mean, unless the context makes it clear otherwise, that what I mean is a vector field. A vector attached to each point in space-time. Okay, so I'd now like to tell you a different way, an even more geometric way of thinking about vectors. Before I do so, are there any questions? No questions? Okay. So, another, perhaps more intrinsic way of thinking about vectors is that a vector can also be thought of as a differential operator. So what do I mean when I say that? So here's what I mean. So let's imagine that we have a scalar and a vector whose components in a given coordinate system x mu can be written as v mu. Then we can define the following object, which I'll just call v, without an index on it, which is the sum over mu of v mu d by dx mu. So this is a differential operator. It's the sum of the 4 derivatives d by dx mu contracted with v mu. So remember my rule that whenever we have a upper index x mu in the denominator of a derivative, we treat that as a lower index. So the symbol that I have written here, v mu d by dx mu summed over mu, is consistent with the Einstein summation notation. And in general, I will be lazy when I write this, and I'll often just write this as v mu d mu. So d mu is just shorthand for d by dx mu. Just a second. So what's the use of this differential operator? Well, if f is a scalar, then I can act on f with this differential operator. And my claim is that if f is a scalar and v is a vector, then vf is a scalar. So this is a nice thing to think about because it takes scalars to scalars. So it's a differential operator that takes a scalar to a scalar. So let's check that. So vf is v mu d by dx mu of f. And so we can then ask what that looks like in the primed coordinate system. So in the primed coordinate system, vf is equal to v mu prime d by d x mu prime times f written in the x prime coordinate system. So in order to understand how that could be equal to the quantity that we've written above, we just use first the transformation rule for the vector here. So v mu prime is equal to v mu times dx mu prime by dx mu, or I'll call it dx mu. That is the transformation rule for a vector. Then I can regard f as a function, x mu prime here as a function of the x mu coordinates, and use the chain rule to compute this set of partial derivatives. And I get df, let's write it in the following way. I get df by dx mu times dx mu by dx mu prime. That's just the chain rule. And what do we have here? Well, this guy is just the vector written in the x mu coordinates. This is df by dx nu in the x nu coordinates. And then we have two Jacobian factors here. However, as you hopefully learned on your last problem set, dx mu prime by dx mu is the inverse of the Jacobian dx mu by dx mu prime. So when you multiply these two Jacobians together, you get the identity matrix and they cancel out. So let's just check that. So dx mu prime by dx mu times dx mu, I'm sorry, did I? Yeah. So let me, I had a nu there. Nu by dx mu prime, that is just by the chain rule equal to dx nu by dx mu, which is equal to 1 if mu is equal to nu, and 0 otherwise. So that's given by the symbol that we usually call delta mu nu, which is the symbol known as the Kronecker delta symbol, defined to be equal to 1 if mu is equal to mu, and 0 otherwise. So that's just another way of saying that these two guys are matrix inverses of one another, so that Vf is equal to V mu times delta mu nu times d by d x nu of f. And if you stare at it for a few minutes, you'll see that this, of course, is just the same thing as V mu d by d x mu of f, which is the previous expression that we wrote up here for V acting on F. So in that last step, I of course used the fact that delta nu mu is equal to 0 unless nu is equal to mu. So that V mu delta nu mu d by dx nu is V mu d by dx mu. So what that means is that Vf is indeed a scalar. Namely, it doesn't pick up any uncomfortable Jacobian factors under this change of coordinates. And so V can be regarded as a differential operator that acts on scalars. Are there any questions? There was a question up here. Yes?
What vector field? You said it's a vector attached to which point in space-time?
Yes.
Along the curve? Or?
No. You can use curves as one way of defining vectors, or you could just define some vector. You don't need to, there are ways of defining vectors aside from defining curves. I could hand you a space-time and some coordinate system, and I could just say, consider the vector which has the following form in this coordinate system. Indeed, we frequently do that. There are many ways of considering vectors. And generally speaking, we'll usually be considering a vector field in the sense that there's a vector associated with each point in space. And if you think about it, if you want to use a vector to define a differential operator, it really needs to be a vector field. If it's only defined on a line, then it will really only allow you to take derivatives along the direction of that line. And if you define it at a point, it won't allow you to take derivatives at all. In order to define a vector that allows you to take derivatives in every direction, it really needs to be defined everywhere. Or, to say that a little more precisely, if V is the tangent vector to a curve, then the differential operator that I have defined is the thing which takes the derivative along that curve. So that's probably worth saying precisely. So if V mu is dx mu by d lambda is the tangent vector along a curve, then the differential operator V, which I defined as V mu d by dx mu, what is that? That is dx mu by d lambda times d by d lambda, d by dx mu, which by the chain rule is just d by d lambda. Right? You just cancel the x mu's. That's all you ever do in the chain rule. So if you have a function, if you have a scalar in space-time, and we got some curve, and you want to take the derivative of that function along the curve, well, you take f, you write it as a function, you take f of x mu, you write x mu as a function of lambda, and you take d by d lambda. And all I'm saying here is that that's equal to vf. That's just a fancy way of writing vf. Or rather, vf might be a fancy way of writing that. Sorry, maybe I've made things more confusing. But hopefully the idea that vectors can be thought of as differential operators is clear. Now, usually in your vector calculus classes, you didn't really think of vectors as differential operators. If you had, you would have associated in vector calculus we can use a vector v to define the differential operator, which is v dotted into the gradient operator. And that takes a scalar function to a scalar function in the sense that you're used to in your previous encounters with vector calculus. Any questions? So, I've actually done something rather subtle here when I wrote the symbol v equals to v mu d by dx mu. And the reason is that I'm writing down an expression for a vector, v, but I'm writing down an expression over here which doesn't actually have any indices. And so what that means is that what I'm doing when I write that expression is I'm thinking of the four quantities d by dx mu as a basis for my vectors. So we think of these d by dx mu as a set of four basis vectors that I use to write all of my vectors in a particular coordinate system. So, for example, in your usual classes on vector calculus, you often have an abstract symbol for a vector, v with the little vector symbol on top of it. And if you wish to write those coordinates in a particular basis, you would write those coordinates as vi, where I runs from 1 up to 3, say, if you're in 3 dimensions. And then if you have some set of basis vectors, then the basis vectors would be given by E, and they'd be labeled by an index I that runs over the 3 different bases, say, x, y, and z. And then the components of the vector in that basis would be given by the formula v is equal to vi contracted with ei. And so one can view the symbol that I have written here, v is equal to v mu, d by dx mu, in a similar spirit, where I think of the d mu's as a set of 4 quantities, or a set of d quantities labeled by the index mu, which are the basis vectors, and the v mu's are the components of the vector in that basis. Are there any questions on that? Thinking in a basis-independent way will take a little bit of practice. It's not the sort of thing that you might become comfortable with instantaneously, but you'll get used to it, and it's a very nice way of thinking about vectors and other sorts of tensors. Yes, question?
You wanted us to geometrically interpret vectors. How are we supposed to geometrically interpret d by dx mu?
D by dx mu is, let's think about it. In the x mu coordinate system, let's say mu runs from 0 up to 3. Then d by d0 is the vector with components 1, 0, 0, 0 in this coordinate system. So it's the vector that points in the x0 direction. It's the unit vector that points in the x0 direction. Likewise, d sub 1 is the unit vector that points in the x1 direction, and so on and so forth. You're supposed to think of it in precise analogy with this expression up here. We don't usually regard those basis vectors as differential operators, but you sure could have in your vector calculus class. Good question. Other questions? No questions? Going once, twice? Excellent. Okay, we now understand vectors. So let's move on to other tensors. So I'm not going to go ahead and assault you with the most general definition of a tensor quite yet. I will, don't worry. The next sort of tensor that I would like to consider is a set of tensors that are equally interesting as vectors, and they go under the name of one-forms. So a one-form, or alternatively known as a covariant vector, as opposed to a contravariant vector, is also a set of D functions. It's a set of D functions which transform in a specified way under a coordinate transformation, just as a vector or a contravariant vector was a set of D functions which transformed in a specified way under a coordinate transformation. Except now, one-forms or covariant vectors carry a lower index in the rather than an upper index, And if you wish to write a one form in a new coordinate system, then you would write it as W mu prime, which is equal to the Jacobian matrix dx mu by dx mu prime times W mu, summed over mu. So you can see that this definition looks confusingly similar to the definition of a vector. But if you pay careful attention to where I've placed and not placed my primes, you'll see that I'm writing down not the Jacobian here, but the inverse Jacobian, the derivative of the x mu's with respect to the x mu primes, rather than the derivative of the x mu primes with respect to the x mu's. So this is the precise sense in which a one form transforms in the exact opposite way as a vector. And as you might suspect, whereas a vector is referred to as a 1-0 tensor, a one form is a 0, 1 tensor. You can probably see where this is going. Now, why are one forms useful? Why do we do something so pedantic as to discuss one forms and vectors separately, one of which transforms using a Jacobian, and another of which transforms using an inverse Jacobian? This is useful because a vector and a one form can be combined to make a scalar. So what do I mean when I say that? Well, if I have a vector whose components are v mu in one coordinate system, and a one form whose components are w mu in that same coordinate system, then I could form the sum v mu w mu summed over mu, and my claim is that this is a scalar. So let's check that this is a scalar. So if this is the expression in the x mu coordinates, then in the x mu prime coordinates, it's given by v mu prime, w mu prime, which using our transformation rules for vectors in one forms is equal to v mu times dx mu prime by dx mu times w. I don't want to mix my indices up before their time, so I'll call this Jacobian matrix dx nu by dx mu prime times w nu. This Jacobian matrix is the inverse of that matrix, giving me the Kronecker delta symbol, delta mu nu, so that in fact mu is equal to nu in this expression, and that I have v mu contracted with w mu. V mu, w mu summed over mu. And so we see, indeed, that the quantity v mu, w mu is a scalar. That's nice because, in general, if you have two vectors, there's no way of combining those vectors in order to make a scalar. You can only do that if you have a vector in a one form. So, formally speaking, in fact, this is how a mathematician would define a one form. So, formally, one can define a one form as something which takes a vector to a scalar. Formally speaking, a mathematician would define a one form as a linear map that takes vectors to scalars. Now, that's a lovely formal definition. It gives little intuition for what a one form actually is. So I've presented, I think, a slightly more physical way of thinking about one forms. There is a bit of language associated with this idea, however, that one-forms combine with vectors to make scalars. So one-forms are also sometimes referred to as dual vectors. And just as vectors live in a tangent space, one-forms live in what is referred to as the dual tangent space, which is referred to sometimes as TPM star, where the star reminds us that we're using the word dual here. Now, all this business about duals and dual tangent spaces is not going to be particularly relevant or important for what we're going to do in this class, but it is language you might run into at some point. Now, when you studied linear algebra and you studied vector calculus, you've already met one-forms. You already met covariant vectors. Whereas in linear algebra, a vector, or a standard contravariant vector, is a column vector. A one-form is a row vector. What is the scalar that one forms using a column vector and a row vector? It's just the dot product. So what we call V mu W mu here would, in the language of linear algebra, be written as the column vector made up of the components of V, D, times the row vector made up of the components of the one form. I wrote them in the wrong order. Okay. I guess I'll be... Yeah, that's a different sort of... never mind. We'll meet that guy eventually. So this is just the usual dot product. Usually in linear algebra and in vector calculus, the dot product is defined between two vectors and not between a vector and a one-form. That's because in your vector calculus classes, you never distinguished between one-forms and vectors. That's the whole reason why in your vector calculus classes, you were never careful about whether you had an upper index or a lower index. Whereas in this class, I've been extremely neurotic about where upper indices live and where lower indices live. The reason is that in your linear algebra class, you are only ever dealing with flat space, where it's reasonably safe to squint a little bit and not distinguish between one-forms and vectors. But as we will see quite explicitly in the next few lectures, in more general cases where we have curved spacetimes, it's absolutely crucial to maintain a careful distinction between vectors and one-forms, and between lower indices and upper indices. And indeed, it's precisely this distinction, which is why we're always so careful only to ever sum over a single lower index contracted with a single upper index. Any questions? Yes?
If you switch multiplication and multiply one term by vector, we just get another vector?
If I switch the order of multiplication, you get what people call the exterior multiplication instead of the interior multiplication. And, what happens if you switch the order of these two guys and use the usual rules of matrix multiplication? Well, you get a whole matrix. You get a set of d-squared quantities, which are the quantities v mu w nu, where mu and nu are free indices. So that's sometimes referred to as the exterior product, and the inner product is sometimes referred to as the interior product. That's a language that we don't necessarily need to use in this class. Yes?
I thought this was commutative.
Matrix multiplication is not commutative. The dot product is commutative, because when we use the dot product symbol, we're implicitly treating these both, if you know what I mean, we're implicitly treating these both as column vectors and just multiplying the individual entries with one another. But when I write it this way, the reason when I say that a vector is distinguishing between upper and lower indices is the same as distinguishing between row vectors and column vectors. When you write a symbol like this one here in your vector calculus class, you implicitly, you treat them all as row vectors, but you define a different operation where you take v1 times w1 plus v2 times w2 and so on and so forth. When I write the dot product in the way that I've done here, I've written it using the rules of matrix multiplication. Matrix multiplication is not commutative. A row vector times a column vector using matrix multiplication is not the same as the column vector times the row vector. Try it out. Multiply a column vector times a row vector, you get a whole d by d matrix worth of stuff, which is sometimes referred to as the exterior product rather than the interior product. We'll meet a version of the exterior product quite soon. Well, I've just told you what the exterior product is. We'll spend much more time with various versions of the exterior product soon enough. Good questions. Any other questions? Yes.
So UW.
Yes.
Here you can define, but WV.
Well, there are different notations that we use in different contexts. So I, in this course, will always use index notation. So when I, in this course, write the symbol v mu w mu, where v mu is a vector and w mu is a one form, I mean the scalar that is formed by summing over mu. Okay, that's what I mean. However, if I were to use matrix notation, linear algebra notation, then you could let v denote a column vector, and you could let v1 denote a column vector and v2 denote another column vector. And then you could talk about something like v1 transpose, which is a row vector. And then there's a bunch of different things that you could talk about. You could talk about v1 transpose multiplied by v2 using the usual rules of matrix multiplication. That is what we usually refer to as v1 dot v2. But you could also try things like v2 times v1 transpose using the usual rules of matrix multiplication.
Okay,
but the reason why I use index notation is because it's always completely clear exactly what I'm talking about.
okay. So
Yes.
how do you, or where do you want matrix?
Okay?
How do you do that?
In
Uh,
yes. If I want a matrix is a set of d squared quantities. So I haven't told you precisely what I mean by a matrix. Usually what you mean by a matrix is a tensor, a quantity with two indices. So one quantity with two indices I could define is the quantity v mu, w nu. Okay? Where mu and nu are now free indices that run from 1 up to d, or 0 up to 3, or whatever. That's even simpler than summing over mu. It's just that set of quantities. And my claim is that if you work out this expression here, you'll see that, in fact, it's the same as this guy. I'll leave that as an exercise. I encourage you to work that out. It's an illustrative exercise.
It's commutative, but the indices, where they go, is not.
The location of the indices, the location and position of the indices always matters. V mu and W nu are numbers. They always commute. One of the advantages of using index notation is that I never have to worry about whether multiplication commutes or not. When you're talking about matrices or differential operators or whatever, they don't always commute. But if you use index notation, everything commutes. Everything's just a number. They're just numbers that are the coordinates of something in a given basis. It's only when you start dropping indices, as we do when we write a vector with a v symbol or a matrix using bold notation, It's only then you have to start worrying about whether things commute. Sometimes it's good to use one, sometimes it's good to use the other. In this class, I mostly use index notation, but not always. Often it's very useful to write down formulas only involving the index-free notation. So I'll often just write down something involving v. So for example, here's a great question. If v is a vector, if v1 is a vector, if v is a vector, and if u is another vector, I can define these two differential operators, and those two differential operators don't commute, so I can define the commutator of those two differential operators, which is another differential operator that doesn't commute. So you can take two differential operators, define their commutator, it's another differential operator. What is that differential operator? Is it a vector? Is it not a vector? It's a mystery. You'll find out on the next problem set. Any other questions? Okay. Now, I told you in our discussion of vectors that, in fact, we'd already met some vectors in this class, although I hadn't been careful to label them as such. Likewise, we've already met some one-forms in this class. Even though this class is only 2 weeks old, we've already met some one-forms. I just didn't introduce them to you as one-forms. But we did, in fact, meet some one-forms. So let's understand what those one-forms were. So let's imagine that I have a scalar, f, which could be written as f of x mu in the x mu coordinate system. Then we could define this following set of d quantities. We could define the quantities df by dx mu. This is a set of d quantities with a lower mu index, according to our rules. Sometimes I'll use a notation, as I said before, and refer to this as d mu of f. Sometimes, in fact, I will be even lazier, although you didn't think that was possible. Sometimes I will be even lazier and use the notation f with a subscript comma mu to refer to this derivative. This is really, I think, the maximally lazy notation possible. Actually, that's not true. The Penrose index notation is even lazier, but beyond the scope of this course. So this is a set of d quantities associated with a scalar. And my claim is that these d quantities transform as a one-form. So let's check that. So let's compute them in a new coordinate system. So my claim is that this is a one-form. So in a new coordinate system, we would have the quantities df by dx mu prime, which, and you can probably guess how this is going to go now, can be related to the components in the x mu coordinate system by using the chain rule, by simply regarding the x mu primes as functions of the x mu's. So this is df by dx mu times dx mu, by dx mu prime. And we recognize this as the components of the one form in the x mu coordinates, and this as the Jacobian that appears in the definition of the one form. So indeed, we see that the set of d quantities, which are the derivatives of a scalar with respect to the coordinates, transform as a one form. So indeed, we've met lots of one forms in our lives. Anytime we've ever taken a derivative of a scalar, that's been a one form. So for example, in your classes on vector calculus, you would write down symbols like a scalar f, and then you would take a set of three derivatives of f that you would call the gradient of f. And that's a set of three quantities that transform in a particular way, you called those a vector in your vector calculus class. In fact, that's a one form, not a vector, if one wanted to be precise about it. Now, it was very convenient for us to think of vectors in a geometric way, and in a way which is independent of a given coordinate system. And so similarly, we will sometimes write one forms in a coordinate independent way. So just as V, we could think of a vector as a geometric object, which is the differential operator V mu d by dx mu. We need to ask if there are any differential quantities which have an upper index rather than a lower index, which transform in the correct way to be regarded as a basis of one forms. And if you think about it, you have already encountered such an object. So, indeed, we will write a one form in a coordinate independent way as W mu dx mu, where dx mu is an infinitesimal displacement of the x mu coordinates. Okay, I don't know. That word is displacement. And the word before it is infinitesimal, abbreviated INF, period. And so just as the set of derivative operators, d mu, can be regarded as a basis for the tangent space, these set of four infinitesimal displacements can be regarded as a basis for the dual tangent space, or the cotangent space, as it's sometimes called, TPM star. And indeed, let's check that this is a reasonable thing to do by understanding what this would look like in a different coordinate system. So if we were to look at this in a different coordinate system, we would write the symbol W mu prime dx mu prime and ask how this could be related to W mu dx mu in the original coordinate system. We use the transformation law. So we use the transformation law for W mu prime. That's the definition of the transformation law for the one form. So that's equal to W mu dx mu by dx mu prime. And then, let's not call that mu prime. It's not mu prime. Not yet. Let's call it dx mu prime. And what's this guy here? Well, we've already worked out the transformation rule for the infinitesimal displacements dx mu. That's equal to, let's call it dx nu times dx mu prime. Oh, I'm sorry, there was a mu. This is mu prime, not nu prime. By dx nu. Again, we have a Jacobian, an inverse Jacobian. They cancel, give me a Kronecker delta symbol, and I get W mu dx mu. So, just as the four derivative operators, d0, d1, d2, and d3, form a basis for my set of vectors, the four differentials, dx0, dx1, dx2, and dx3, form a basis for my set of one forms. And there's an additional piece of notation that I would like to introduce. Before I do so, let me pause and see if there are any questions. I realize that there's a sense in which everything I'm doing is completely trivial, and a sense in which everything I'm doing is completely confusing. They're both right. So some of this business of Jacobian's chain rules whipping around dx's and deltas, it just takes a little bit of getting used to. Yes, question?
If you take the product omega v,
Yes.
and the index negative, you would cover the scalar product?
Yes. Wait, Oh, sorry, you mean using this differential operator notation? No, you need to be more careful. Yeah. V regarded as a differential operator, one needs to be more careful. We'll discuss. There are various, using index-free notation is sometimes useful, sometimes not. For certain tensors, known as differential forms, there's an extremely slick and highly useful set of derivatives and multiplications that we can use and that will work out. We'll burn those bridges when we come to them. Yes. Other questions? Okay. Now, I would like to introduce, so I've introduced a lot of really slick notation. I'd like to blow your mind just a little bit more and introduce one more neat piece of notation. So, for the one form defined above, f mu, or d mu of f, so this is the one form whose components are given by the derivatives of the scalar f, we have a special notation. So this one form can be written in index-free notation as d mu f dx mu, or df by dx mu. And so the special notation that I would like to introduce is the obvious notation where we cancel dx mu by dx mu and just write this as df. In fact, this notation will become a lot clearer in the next few lectures when I reveal to you that for your entire lives as physicists you've been lied to, and you've thought of symbols like dx1, dx2, and so forth just as infinitesimal displacements, but in fact they should be regarded as one forms. And they should be regarded as special one forms where this guy d here is not a symbol that stands for displacement, but rather is a special differential operator that we will define. And f here is a scalar function. So, for example, let's imagine that we have space-time described by some coordinates x0, x1, x2, and x3. And I could define the function which is given by x0 in those coordinates. It would take some other form in some other coordinates, but that's the function, that's the form of the function in these coordinates. Then I could define the one form which is given by the set of d derivatives of the function f. So what are the set of the d derivatives, d by dx mu, of the function f? Well, that's equal to 1 if mu is equal to 0, and 0 otherwise. And we have a special name for that one form. We call that one form dx0. So that is the special notation that I will use for this one form. And in fact, whenever you in your lives have used dx0 as the name for the infinitesimal displacement of the coordinate x0, what you really have been doing is talking about the one form dx0. And all of the rules of vector calculus that you learned for manipulating derivatives, measures, and so forth follow from the rules of tensor calculus that one uses to manipulate tensors. Yes?
dx0 is a one form, you said?
dx0 is a one form.
But it has an upper index.
Yes, it does.
Okay.
So this is an important thing that I'm trying to be very careful here because I know it's easy to get confused here. dx mu is a set of 4 one forms labeled by the index mu. But I'm using an index-free notation. So dx0 is a one form. I'm using an index-free notation where I'm not writing the index explicitly. If I were to write the index explicitly, I would write this as delta 0 mu dx mu. So it's the one form whose components are given by that guy in the x mu coordinate system. Now, yes, so it's very easy. It's easy to get confused in the beginning when you're not used to this stuff. So the only thing I can recommend that you do is start reading the textbook, start working through problems. Even though I gave you a little extra time on your next problem set, you could start trying to attack it this weekend and getting used to this notation. Likewise, for example, if f is equal to x1, you could define the one form dx1, and indeed, if f is some more complicated function of the coordinates in this particular coordinate system, you have more complicated differential forms, and all of the usual rules that we have worked out involving the transformation laws of these infinitesimal displacements are nothing more and nothing less than the transformation rules for a one form. Any questions before I continue? No questions? All right. It's time to stop beating around the bush. We've met 0, 0 tensors, 1, 0 tensors, and even 0, 1 tensors. We've now grown up, and it's time to define a tensor. So what is a tensor? A k, L tensor, where k and L are non-negative integers, 0, 1, 2, and so forth, is a set of d to the k plus L functions which could be written in a given coordinate system as t mu 1 up to mu k, mu 1 up to mu L, which transform as follows. So if you want to write t in a new primed coordinate system, then it would take the form t mu 1 prime up to mu k prime, mu 1 prime up to mu L prime. And this is related to the d to the k plus L functions in the unprimed coordinate system by the multiplication by k Jacobians and L inverse Jacobians, one for each index. So we would have dx mu prime, mu 1 prime by dx mu 1 times dx all the way up to dx mu k prime by dx mu k. And likewise for the covariant lower indices, dx mu 1 by dx mu 1 prime all the way up to dx mu L over dx mu L prime times t mu 1 up to mu k, mu 1 up to mu L. Sorry, I've written it in 3 separate lines. I guess I should have, but they're all multiplied. And it's worth pausing to stare at this expression for a second. So this might look like a complicated expression at first, but if you think about it for a little while, this is really the only possible expression that you could write down. What we're doing here when I write down the right-hand side of this equation is I'm balancing the indices in the only way that's possible. So remember that when I write down dx mu 1 prime by dx mu, that's a quantity with one upper and one lower index. And that mu 1 lower index has to get summed over with the mu 1 upper index here. And likewise, the mu 2 index gets summed with the mu 2 index and so on and so forth. And then for the lower indices, I need to multiply by the inverse Jacobian, because that's the only way that I could balance the indices and sum over them in a way that's consistent with Einstein's summation notation. The beauty of Einstein's summation notation is that it makes it very difficult to write down an incorrect equation. Not impossible, unfortunately, but it makes it very difficult to write down an incorrect equation as long as you're careful about scrupulously following the rules of Einstein's summation notation. So the principle that one follows in writing down these equations is that one balances the indices. In general, in this class, it's a very good idea to get used to looking at formulas and making sure that you understand what the free indices are, what indices are summed over, and that only proper indices, namely one upper and one lower index, are summed over. Now, what I would like to proceed and do is then talk a little bit more generally about tensors and what the various operations one can do on tensors, and define various other sorts of special kinds of tensors, metric tensors, differential forms, and so forth. That's what we'll proceed to do next time. So next class we'll discuss tensors in all of their full gory detail, before proceeding in the following class to start developing the calculus of tensors. Taking derivatives of tensors, we'll move on to geodesics, metrics, curvature, and so forth. Before I stop, are there any questions? All right, thank you. See you on Monday.